All right, so our next and third speaker today is one only Don Burkhoff. Don is co-founder and CEO of TruWeather Solutions. Don has deep expertise synthesizing complex weather data sets into simple decision insight for operators for unmanned autonomous systems, ground transportation, logistics industries, and the emergency management community. He is an Air Force veteran with 35 years experience in weather industry and logistics systems, including a year serving as the Expeditionary Base Commander at Manas Air Base, Kyrgyzstan. He designed and led regional and global aviation weather operations centers, responsible for providing aviation weather services to over 200,000 Air Force and Army missions worldwide. A distinguished meteorologist and technologist, he led the National Weather Service Directorate for Science and Technology from 2008 to 2012. Please welcome Mr. Dan Burkhoff. And stand by one, Dan, or Don, and I will get that to you.
Okay.
I see your slides. Go to presentation. We're good.
Okay, thanks, Rex. Welcome, everyone, and thank you, Vertical Lift Society, for putting this on today. First of all, I'm awed by the work of the folks that talked in front of me today. As most of you know, the weather industry is a family, and we work these problems together. I'm now in the private sector. I was in the government for 28 years. I've had the pleasure of working with some of our great research institutions, such as NCAR and Mateus, and working within the National Weather Service with the Aviation Weather Center. So I think it's important to understand that we are working this together and trying to figure out how do we bring the best outcomes to attack this problem. And so I think that's an important takeaway today. As an operator with an operator view of things, I'm going to take a little different approach to my presentation because I leave the expertise up to Mateus to figure out all the challenges and how to solve them scientifically. I will say that there's a couple things I want to mention. Some folks may be asking why, I fly helicopters today in the city and, we don't have these big issues. And I say the answer to that is that's true. However, what we're talking about in the future is a high density operations environment based on very tight scheduling and moving people around. And when I think about this idea of urban air mobility and carrying people to the airport or to the train station and having them align with a driver on the ground or catching an airplane in JFK and being there on time and just in time, what we need is, the environment we work in today with the tools we have are just not going to be able to, really support that scalable business model that people have a vision for. And I think that's one of the important takeaways, because even the great work that Rex has done with the HEMS tool and working with the Aviation Weather Center, most of the data is going to have to be machine to machine shared in the future. We're not going to have necessarily pilots in every case watching the weather for every route for every mission. In the cases of small UAS, we could be flying many drones, many autonomous vehicles with just one person potentially sitting in an operations center and just watching for things that are not going well and mitigating and working through those. We're not going to have somebody that's going to be able to go through and sift their way through lots of data to figure out if they're going to have fog and stratus over Sheepshead Bay in Brooklyn when they're flying from downtown Manhattan to JFK. And it could be the only fog in that route is subgrid, as Mateus said, over Sheepshead Bay. So these are, the challenges that, I'm looking at as somebody who's looking at bringing a private sector approach to this, working with the government and working with the research community. So I think the first thing is weather impacts all our decisions. A lot of us, it's second nature. For experienced pilots, it's second nature. But there's a lot of folks out there today flying drones that don't have that experience that some of the pilots out there have in weather. and understanding the atmosphere and some of the things Mateus talked about, it's important to have a context. And, you know, when weather impacts our decisions, when we care about it is only when it actually impacts the application we're doing at the time and the place that we're trying to do it. And many times there's folks that think weather is just the price of doing business, it's something that, we can't control. But the truth is there's a lot of good data out there that can be used in planning and execution that can foresee and mitigate problems before they occur. And I think that's what, where we're coming from, especially in the private sector, knowing that we know that business models for running these operations are going to be so critical to the operators themselves, and they can't afford to sit on the ground because we think there's something in the air, or they can't afford to not know how the weather is going to impact them in 4 hours from now, because they've got to give their client assuredness that they are going to get from downtown Manhattan to JFK with 5 hours lead time. So these are the things that, that I think about. And when you look at this chart here, what you see is you're going to see a very complex system with a lot of different moving pieces. And I think the one thread that we need to try to understand through all of this is that consistent, precise, and resolute weather data and information and decision tools are going to be absolutely critical for a well-functioning and non-chaotic airspace. So, Mateus did a great job of pointing out all the local challenges and local effects that are not even really addressed today in any of our products. And part of that is because we've never had a business case or a need as strong as we have right now to be as good as we are. Most of our manned aviation aircraft and the people who fly in them were able to deal with a lot of these bumps and bruises they got along the way when weather data wasn't quite as accurate as we had thought it would be or hoped it would be. But when you don't have aviators on an aircraft, and when you're flying aircraft that are much more weather sensitive, and you're flying them in the boundary layer near buildings and structures that are going to cause turbulence, and you have differential heating, like Mateus pointed out, between the downtown area and the water, these are things that are going to become impactful. And when MIT Lincoln Lab, they conducted this study funded by the FAA, and they demonstrated that this is the report card we have right now on how current available aviation sources rate for UAS needs. And this is something that is going to become more recognized and more impactful to people's business model and revenue as they start trying to schedule more flights, jamming more operations into a smaller envelope, not carefully managing each flight for demonstration and avoiding the weather to make it work, and not flying in places where the weather is always good to demonstrate what they can do. The reality is that reality is going to at some point hit the industry, and we want to do is here as the weather group is we want to get ahead of this problem, and to do that we need operators support, and we need to demonstrate the need for research dollars, and to recognize that the roles of SDSPs, especially these are supplemental data service providers, especially as they're being integrated into the unmanned area traffic management systems, they need to be also integrated into the planning and the ConOps development around all these infrastructure that's being built to support these systems. So, I guess I'm going to take a higher view, but it all starts with observations. And, our models are only as good as how much density of observations, especially in situ and remote sensing observations there are, to understand what the atmosphere is actually trying to tell us it's doing right now. We have so much uncertainty even in just trying to understand what the atmosphere is doing right now, that we prepare our models in a way where we make a lot of assumptions right out of the box. And that initial depiction of what we view as the atmosphere looking like is already an assumption. And there's already errors in that going into a model that is also just a model. And that model also doesn't account for all the aspects of everything that happens that causes weather to occur. I mean, we're getting better at it. our science is better, much better than it was. And I would almost argue our science is probably ahead of where we are in terms of being able to give enough observations and in our computing power. So computing power, science, and observations make a forecast. And, we need focus on all those areas, especially now when we add the fourth dimension, which are man-made buildings and structures that aren't in our atmospheric models, don't even know they're there. So now we get into the area of computational fluid dynamics and coupling. So TruWeather and we've been out here about 2 years. We're in the New York State test range. We're on several contracts now with the FAA as a sub to do some work in the UTM arena. We're working in the state of Ohio and been hired to help them develop their unmanned aerial system traffic management. We've been out supporting operations. We just completed support for an operation from the islands south of South Korea, where they delivered masks, 8.8 kilometer BV-LOS mission. And we're learning a lot as we're out there about the impacts and what kind of data we have and what kind of data we're really going to need to be effective. And I think, the one point I want to make is the weather's never a problem until it's a problem. And so, 90% of the time, you may not have a problem. It's only that 10% of the time that you may have a problem, but that's when your world falls apart. And we need to make sure that, we have processes, techniques, procedures, even within the operations world, and better training for them on how to deal with these microclimate problems that pop up that can cause your battery to run out faster, cause you to have some stability control issues and other things. What we have found is that Part 107 and Part 135, the weather training, and I know this because I built a module for somebody to do the weather training in Part 107, and it's woefully inadequate for the missions that we're training our pilots, asking our pilots to do. And the requirements also for what the weather, what the weather information required for them to fly is also pretty inadequate. And again, this is not anybody's fault. We're trying to grow this community quickly. And for the most part, we cut and pasted manned aviation weather requirements into Part 107 and 135. And so, what we have now is a situation where we need to go in and figure out, what do we really need to do and require, and what are those performance requirements? And then the other challenge that we see is, folks, generally the threats that are capturing people are the things you can't see, right? Like winds aloft, turbulence, icing, thermals, as Mateus was pointing out over the city. If you're flying a light UAS with a wingspan that's a little larger, you're going to get dislodged potentially by some strong updrafts in the summertime. And, how does this impact airspace management, separation, deconfliction? These are things that, as I've been working in the industry, I'm starting to recognize and think about. And because, we're also involved in working with the Swiss U-Space group and also ASTM F-38, and we sit in a lot of the meetings with the UTM service suppliers and others to talk about, what are all the pieces have to come together to have a smooth operating ecosystem. And, these are the types of things that I think, we need to be paying attention to make that happen. Mateus, went into a great deal of detail about the City Canyon problem. And I think that, the way I view the problem is, we've got to have something that gets us better intelligence than we have today, which is nothing. We really don't have any operational capabilities that are sustainable and can support large scale operations right now in a city of small UAS and eVTOLs. And we need to, the first step is getting something that allows us to identify hotspots just so we can keep people away from those areas. The second step is to get the sensing and the better information integrated into the science so that we can improve upon that and get, a little bit better handle and understanding of specifically where these areas will reside within the urban area. And then I think finally we need to reach the plateau that Mateus was talking about, which is really getting into understanding how these thermals and eddies are flowing during different parts of the day at different altitudes, and making that, that ultimately would be the system we'd all, are seeking to do. And it's going to require, more sensing, better models, and it's going to require also some machine learning and other techniques. I think it's going to require IoT data sets that are good enough. I think we got to make sure that, we don't get backed into a corner where we think we have to have an ASOS quality observation on every street corner, because that's not going to happen. We've got to keep sensing affordable so that we can encourage and incentivize the private sector to put sensors out there and provide data that the SDSPs can take and use and upgrade their products. And I believe we're looking at a model of fees for UAS operators and eVTOL operators that would come through the UTM service suppliers that go back into the system and help support some of this infrastructure that I don't believe the government's going to be able to do on their own, especially right now with the deficits and the other issues we have on our plate. So what are the urban weather challenges? I think, again, Mateus, outlined it very, very well. So I'm just going to focus on operationally what I think are important to figure out, right? These invisible threats, above ground level and above ground level, the turbulent eddies that can cause stabilization control impacts, Ventura effects, where we have rapid changes in wind speed and direction over very short distances that are caused by buildings and not by the atmosphere. Microburst translation, what happens, if you have a collapsing storm, especially out in the desert areas where, you can have a translation of winds can travel, 10s or 20s or 100 miles and hits an urban canyon and then starts getting all chaotic within that canyon. That's not something that we have the ability today to forecast in our model. We don't even have the ability to hit the microburst forecast without it already either in the process of occurring or some very good tools that say it is going to occur. So these are areas that, microbursts are something that, or any of these are something that can change rapidly. So, one of the things that folks always say to me, pilots say, we just need, these are only 10 or 20-minute flights or half-hour flights, we could, the weather doesn't change that fast. Well, that's probably the case 99.5% of the time. But, there was a snow squall event that went through New York City several months back, and I talked to people who told me that absolutely killed their ability to get chaos under control, moving people around in air. And so, things happen and you got to plan on it and you got to know how you're going to deal with it. It doesn't mean we're going to be able to forecast it all right away or perfectly, but we just got to understand that it is a problem that is going to be something that has to be worked with and mitigated and addressed over time. And we need to plan that into our system so that, over time we get better at it and we can start mitigating those impacts. He's already talked about the subclimate, some subgrid microclimates. And I know that, FAA, once they figure out that unmanned vehicles are flying 10 miles and they're flying through patches of fog that nobody knows is there, they're going to want to know how we're going to improve that capability to give better granular information that people are actually following the flight rules, right, that are required. How do we enforce the flight rules that are required? And then we talked about temperature and, urban heat island, they saw it out in TCL4 out in Reno where the building tops got very hot and they were running into density altitude issues. Again, ambient air temperature is a lot different than building air temperature. When you're only a couple of feet off the ground, that's not ambient air temperature. And so how are we going to understand what those temperatures are and how they're going to change through the day, and how is that going to impact loading and weight and all those things that you got to think about when you're trying to move people and cargo. And so again, talking about cargo and people, the client experience is also a factor in this. You could definitely, these aircraft are going to be built to tolerate a lot. There's no doubt about it. Although I've been told that we're going to have an all-weather aircraft since I joined the Air Force in 1984, and I still haven't seen one yet. But the bottom line is that, these engineering challenges are doable if you have money and you can carry a lot of weight and do things, but it always seems like the business model gets in the way of good engineering sometimes. So we've got to think about, how we're going to impact not just how these aircraft are going to be impacted by the weather themselves and what they can take in terms of airworthiness, but what about putting somebody in it that's going to throw up on the way to the airport? That's not exactly a good client experience, right? So you got to think about things like that. And when I look at Mateus's eddies flying out, coming out of Dallas with a 5 meter per second vertical lift, I know it's not going to be smooth, and people are going to get sick. And if they don't have a good client experience, they're not going to come back, right? So these are things you got to think about in a business, right? And also the decision about how far in advance do you need this data, because most folks that are going to be moving people on demand, they're going to need to have a pretty clear understanding 5 hours in advance if those clients are going to show up, they're going to get them to that airport on time. And so you need to have lead time. This is not just about real-time weather information. This is about a business that needs to have information that will actually dictate whether or not they're going to be able to meet that client contract that they have. And, I talked a little bit about airport METAR temperatures versus, downtown, big difference. You can fly from Manhattan to over the Sheepshead Bay and then over to JFK in the summer, and you can go through like 3 major climatic zones, and temperatures will vary, could vary anywhere from 70 degrees to 120 downtown on the skin, right? Because if you have a little, you're over Sheepshead Bay, you have a little sea breeze that hasn't penetrated all the way into New York City because you have a strong southwest flow, but it's enough to get over Sheepshead Bay, and that water temperature is 68 degrees, you're going to have a lot of different temperatures you're dealing with along that route. And then, of course, no human pilot. And it's really difficult. I mean, how much the human pilot does and the inferences it has and the processing it's doing, that person's doing to, deal with all the weather inadequacies we have in accuracy, precision, and measurements is probably not well understood. And it's going to be really hard to replicate that in machine learning for a long time. And again, if there's no pilot on that plane, you're losing a level of capability, right, to deal with these events. And that's something, again, research we should be looking at. And then data latency. We talked earlier about, it's only a 20-minute flight, but, outflow boundaries coming in from thunderstorms that occur 20 miles away, which don't ever even come near your route of flight, pop-up showers, pop-up thunderstorms, localized ceiling and fog, microbursts. These are things that latency is going to be important to measure and get to a decision. And I think, these are some of the things we need to look at also. So, taking on the most difficult challenge first, I think, is really this idea of the cityscape and how we're going to, work through this urban environment problem. And I think, we need to get a project going in a proof of concept and find a city that's willing to play, that says, what can we measure? What can we do to measure and understand the scope of the problem? How do we decide where to put sensors in a city, right? I mean, again, budgets are limited, I mean, even if you can get a municipality to agree, hey, I'll pay for some sensors as part of my smart city initiative. If you ask me or another meteorologist, so how many do you need? I'd say I want one at every street corner. I want one at 10 feet. I want one at 200 feet on every building and around in the middle of the streets and all that, right? That's not going to happen, right? So the question becomes, how do you figure out, where do you start with a sensor coverage that's going to give you a maximum bang for the buck at the lowest cost, but give you some intelligence much better than we have today. You know, and that's kind of like the 80-20 rule in my mind. So it does require a framework, and it requires that we got to start thinking not just about the ultimate solution, but we got to start thinking about intermediary steps. You know, crawl, walk, run. I know it's an old cliche, but it really means something. You know, how do we start a framework and start biting off some of this huge elephant that we have to work through, and doing it in coordinated steps so that we can begin learning and begin solving some problems, even if it's not the perfect solution. And you know, if we can find a way to optimally place sensors in a city, any city, and everyone's going to be different because they all have different, you know, structures and footprints, you know, we can start to, you know, build up a database. We can start doing some coupled, you know, high resolution atmospheric and CFD modeling. We can begin learning, taking the data and improving the system. And, you know, we could start slowly, you know, developing a better solution. This is not something that's going to get solved in even 20 years. This is a long-term effort that's going to probably never be perfect enough in my lifetime, and maybe not even in some of the younger folks' lifetime that are sitting in this webinar, but we have to start somewhere, right? And then of course there's hurdles, right, to all of this, and figuring out how do we begin to sense cities and sense areas. And it starts with, you know, we need communication. And I think the bandwidth for communication is something that is doable if we're not vying for all the communication for all the private, civilians. But there's some of these networks now that are building have dedicated communication bands just for the government services. And I think, you know, we got to make sure that weather data becomes mission critical and mission essential, and that it's recognized as an important component of emergency management and other systems. And then computer processing, of course, is always going to be the long pole in the tent. The challenge is how much can we distribute this computer processing? How much could be edge computing? How much could be products that are developed locally and sent back out locally without going all the way back to the cloud, and just sending back what you need and processing what you need? And we got to think about, you know, this is a whole architecture for weather to think about how do we want to, you know, lay out this IT computer processing infrastructure using modern techniques that are being used within the smart city realm. And then, you know, smart in situ sensors, you know, what kind of sensors do we need? You know, how good do they have to be? What's good enough? How do, you know, where is the placement? So these are things that, you know, we got to work towards, but we also have to make sure that it's affordable and that there's a way to amortize these costs across all users, because the government's not going to pay the bill for it. And the only way you're going to do that is by setting up a public-private partnership approach where there are fees involved and money's flowing back to the sensor owners and others in some way, shape, or form to offset those costs. So you know, I've been, again, working in this for about 2 years, and I've been sitting in the ASTM F38 group for a while, and we managed to get them to recognize that we do need a weather standards group, and they're calling it supplemental data service provider weather standards group. It's important that this group work with the private sector and with the government entities, and we have FAA representatives on this group. Marilyn, who's going to speak next, is on it. We have major companies like Amazon, Airbus, UPS, Uber on it, and we have UTM providers on it. And the goal is to develop, you know, a framework first. We gotta get approval for our tour, terms of reference, which we're working on right now. And that the goal is find a sweet spot where we can drive innovation and not just cut and paste what we've been doing for the last 50 years. Think outside the box a little bit about what's good enough. Come up with those performance standards, maybe based on risk, maybe based on aircraft type, maybe risk profiles, and get those working and get a first set or an initial set of standards that isn't going to solve world hunger, but is going to give us something that's better than what we have today and is also executable. So we don't want standards that are going to be based on science and technology that we're not going to be able to deliver for the next 10 or 15 years. It has to be something that's executable, but realizing that it's going to also evolve and that the first draft tour and the first standards are not going to be the last standards. It's going to be an evolutionary process. And that everything is focused on quality control and quality assurance. We don't have to necessarily certify systems like we have with ASOS. We need to certify data. We need to look at the data and look at, how good the data is and what's good enough, and then potentially use certain data sets for certain decisions based on the quality of that data. And these are, there's just a lot of work to be done here, and there's going to be a lot of folks are welcome to join this group if they would like. You can see my email address on the bottom, and we welcome you. So that's what I have today, Rex, and everyone out there. Thank you for the time today, and I really do again appreciate the smart people that are on this webinar today also presenting. I see a lot of alignment in thinking now, a lot of advancement over the last year in maturing, and now we can start looking at how we can work together to get the maximum effect of all these capabilities and not pull against each other, but work together. Thank you.
Don, thank you very much. Greatly appreciate your insight on this new and burgeoning aviation arena and how weather will need to play such a critical role.